Hello everybody, it's Mr. Arocena, and in today's video I'm going to be talking about one application of magnetic forces called the mass spectrometer. Now the mass spectrometer is a device that chemists and physicists use to determine the size of a particle. And what it basically does is it separates particles by their charge and their mass. So the mass spectrometer consists of three parts. The three regions of a mass spectrometer are as follows. There's the first section. So this section, the beginning of the mass spectrometer is the accelerating region. And then it's followed by a region called the velocity selector. And then the final region is the deflecting region. We'll discuss what each of these regions does. So the accelerating plate, as the name suggests, so the accelerating region, this is the part where the particles are accelerated. So we take the particles of interest, put them in the accelerating plate, and we start them at rest, and then the particles are accelerated through the region and then ejected into the next part of the mass spectrometer. So what happens here is that these plates, these are charged plates, where depending on what what particle we're working with, we'll either charge this one positive and this one negative, or we'll flip them and charge this one negative and this one positive. Regardless, there is a voltage between them, and because the particles are usually charged, they will give the particle some amount of potential energy. Okay, so the difference in charge gives this particle some amount of potential energy. Now, as the particle accelerates through the region, that potential energy gets converted into kinetic energy. So this potential energy gets turned or gets converted to kinetic energy. Let's call it kinetic energy. Now once the particle has, so we can, I guess, rearrange this equation to show that my kinetic energy is equivalent to my potential energy, which is then just voltage times charge. Now this kinetic energy means that the particle, when it leaves here, it'll have some kinetic energy, and then we can use the following equation to determine the mass of that particular particle. Well, at this point, if this is an unknown particle, we don't actually know the mass of the particle. So that's the second region is important for that. The second region is what's known as the velocity selector. In this region, we have two fields. We have an electric field and a magnetic field. And the charged particle, as it moves through this region, will experience forces. Will experience both the electric force and a magnetic force, because as we know, a charged particle in an electric field will be pushed around, and at the same time, because a moving charged particle creates a magnetic field, then it'll experience a magnetic force as well. So the general rule here then is that if my particle, if the magnetic field pushes the particle more, then the particle will get pushed into one of the walls of the velocity selector and then not make it through. If the electric field pushes more, then the particle will get pushed the other direction and get crashed into the wall and doesn't get through. So what the velocity selector does is it makes sure that whatever charge this particle has, the force of the electric field equals the force of the magnetic field. That keeps the particle going straight through the path and out the other side. If any of these, if this force or this force is not equal to the other one, then the particle gets pushed either up or down and then crashes into the walls of the velocity selector and doesn't come out the other side. So what we can do then is we can say, okay, well, I have a moving particle, and the electric field will exert a force on that particle. So electric field is force per charge. So I can rearrange this to show that the electric force, electric force, use capital E, is equal to electric field times Q. Okay. And the magnetic force is equal to QV. So notice that these forces don't actually depend on the mass of the particle, they only depend on the charge. Okay, now because I know that the electric force and the magnetic force have to be equal, I can set the equations equal to each other. So electric force has to equal magnetic force. As you can see, the charge of the particle doesn't actually even matter at this point. The charge doesn't matter. And we can show that if I have a known electric field and a known magnetic field, then I can calculate the velocity of the particle that will be allowed to go through this particular velocity selector. Okay, so this allows me to sort of guarantee that whatever comes out of the velocity selector is traveling at some fixed velocity. Okay. Now the last part of the mass spectrometer is what's known as the deflecting region. The deflecting region only contains a magnetic field, and the purpose of the magnetic field is to bend the path of the particle. As you hopefully remember from earlier when I asked, if I have a magnetic field, doesn't matter, we'll say it's coming out of the page. If I have a magnetic field that is coming out of the page, and I pass a particle through it, so if I have a charged particle flying through it, that charged particle, depending on its charge, will start entering a curved path like so. And the idea behind the deflecting region is that the particle will curve and then it'll collide back to here, and here we'll have, on this part, we'll have a sensor to detect the particle. And then based on the radius of this path, so based on this radius, we can calculate kind of the mass of the particle. Because if you remember, from circular motion, the centripetal force is mv squared over r. So if I can measure this, then I can determine the mass, because the velocity has already been selected based on the velocity selector. So the velocity of the particle is predetermined by the velocity selector, and then we can calculate the centripetal force using mv squared over r. Now what's causing the centripetal force? Well, in this case, the centripetal force is being caused by the magnetic field, and we know that the magnetic field at B is equal to Q times V times B. We already know what this is, and since these two have to be the same, we can say, okay, in this magnetic field region, the magnetic force has to equal the centripetal force. Alright, so let's go through an example of how we can use this mass spectrometer with some data. Alright, so let's suppose we have an electron we're passing through the mass spectrometer. It passes through an electric field of 6.3 times 10 to the 3 newtons per coulomb and a magnetic field of 7.11 times 10 to the negative 1 Tesla. So this is actually, because it's undeflected, this would be in the velocity selector. So this is passing through the velocity selector. Now in the velocity selector, we know that if I'm not being deflected, my magnetic force has to equal my electric field force, or the electric force. So magnetic force is going to be QVB. Electric force is going to be times Q. Now we're asked to find what's the speed. The charges don't actually matter because they will cancel out. So we get the following. Speed will be VB times E. So arranging this, we get the following. Now our speed, our electric field force, 6.3 times 10 to the positive 3 per coulomb. And our magnetic field force, 7.11 times 10 to the negative 1 Tesla. And this will give us the speed in meters per second. So we get a speed of about 8,860 meters per second, or about 8.9 times 10 to the 3 meters per second. So any electron coming out of that velocity selector will be guaranteed to have a speed of this. In actuality, any charged particle coming out of the velocity selector will have this kind of charge. Okay. Alright, so let's go to another example, or the next example. In this example, we're going to be working in the deflecting region. So here we'll have an electron traveling perpendicularly through the magnetic field, deflected in a circular path with some radius, and we're asked to find what's the kinetic energy. So this is in the deflecting region, and in the deflecting region we established a relationship that the centripetal force in the deflecting region has to match the magnetic force that the particle feels. So the centripetal force we know is mv squared over r, and the magnetic force is going to be q times v times b. Now for kinetic energy, down here, we need to know the velocity of the object because it's mv squared. What we're going to end up doing is we're going to have to rearrange this to solve for v. So in doing that, we get the following. V squared equals qvb times r divided by m. We can divide one of the v's out, so we get the following. Velocity of the particle is its charge times b times the radius of its path divided by its mass. Now because we're told it's an electron, we know the mass of the electron. Now this is a known value. We also know the charge of the electron, which is also a known value. So the charge is 1.6 times 10 to the negative 19. We have a magnetic field with a value of 7.2 times 10 to the negative 2. Our radius of our path is 3.7 times 10 to the negative 3, and the mass of the electron is 9.1 times 10 to the 31, I believe. Alright, putting all of these numbers into our calculator, get a speed of approximately 4.7 times 10 to the 7 meters per second. Okay, so now we have the speed of our particle. We can calculate its kinetic energy using this equation. We have the mass of the electron as 9.11. So putting the mass of the electron, so that's the mass of the electron, and the speed of the electron into this equation here, we get the following. We get a kinetic energy of about 1.0 times 10 to the negative 15 joules. Electron volts, that would be, it's about 6,281 electron volts, give or take. So that's what the mass spectrometer allows us to do. So if I know how much energy I am giving the particle, I can then use the equations in the velocity selector and in the deflecting region to kind of determine the mass and the charge of the particle coming out of it. Alright, your assignment now for today will be to complete the following worksheet. The link will be in the description below. If you guys have any questions, you guys know how to contact me.